Okay, now we will be solving the same problem, three-span continuous beam problem, one more time, but in a different method, a more practical method. And it's actually mathematically equivalent to what we were doing. The only difference here is, remember that in the previous problem, we were releasing each node one by one. But here, actually, it doesn't matter. We can release all the nodes at the same time and calculate the carryover moment and transfer it at the same time. It's mathematically equal. Maybe mechanically it's not, doesn't make sense, but mathematically equivalent, and it's a more practical way. So let's see how we can do it. So I call this second way. So I'll draw a similar table. This is point A, B, C, and D. Let's draw our table first. A, B, C, and D. Let's write the distribution factors. So at A we have a fixed support that's 0. At B the distribution factor is 0.428. The distribution factor BC is 0.572. 0.572 here, 0.428 here, and D is a pin support. We will not use it, but this is equal to 1. So now let's write the fixed moment. Remember that this is the case when the values of all degrees of freedoms are equal to 0, and when there are no member and rotation, these are the moments: 128 minus 128, 72 minus 72, and we use modified equations for member CD, and the fixed moment is 108. And remember, this is the case when we clamp, all nodes are clamped. In other words, all the degrees of freedoms are equal to 0. In the previous solution, we were releasing each degrees of freedom one by one, but as I said before, instead of doing that, I will release all the nodes once. So at node B, the unbalanced moment is minus 56. At C, the unbalanced moment is 52. If I can write 52. Yes. Oh, I'm sorry, this was the other solution. Of course, it's not 52. Sorry for that. Let me erase it. It's 36. Okay, now this is the picture. When we release all the nodes, the unbalanced moment at B is minus 56. The unbalanced moment at C is 36. And we will do the distribution at the same time. So when node B rotates, 56 times 0.428 gives me a moment that's equal to 23.97. This is in the opposite direction, it's the resisting moment, 32.03. And here I'll do the same thing. Unbalanced moment is 36. 36 times 0.572 give me the unbalanced moment, opposite direction, minus 20.59 and minus 15.41. So when I release all the nodes, of course this is 0. These are the distributed moments. Release all nodes. Now when I release B, distributed moments, meaning that there's a rotation. So due to that rotation, I'll have carryover moments. So this is the stage where we calculate the carryover moments. It's 11.98. This one is 16.01. 16.01. This one is minus 10.29. Of course, here we don't have any carryover moment to the free pin joint when the node is free to rotate. So at the end of the first cycle, so I call it the first cycle, we distributed moments and we calculated the carryover moments due to that. Now, after the distribution, as you see, we still have some unbalanced moment here. That's equal to 10.29. And at node C, the unbalanced moment is 16.01. This is of course minus. So let's go to the second cycle, distributed moments. So distribute the unbalanced moments one more time. So then I have 4.4 here and 5.88 here. 16, the unbalanced moment at node C. So distribute that, minus 9.16 minus 6.85 and do the carryover moments. Half will go to the fixed support. Of course, this is also 0. Half will go to node C, 2.94. Half here, minus 4. This should be 4. Minus 4.56. So after the second cycle, this is the second cycle. After the second cycle, the unbalanced moment at B is 4 and the unbalanced moment is 3. So I find these moments still large. So I'll continue, go one more cycle, distribute the moments. So this is 0, 4.56, 58. So I got 1.96 here, 2.62 here, minus 1.68, minus 1.26, and carryover moment. Half will go here, 0.98, 1.31, minus 0.84. Okay, after the third cycle, as you see, the unbalanced moments are smaller. So they are in the range of 0.84 or basically 1 kilonewton meters. And if we think that this is enough, we can stop, but we don't stop here. In order to stop, I have to distribute the moments one more time. Distribute the moments. This is 0. All this moment is carried by the support. This is 0.36. This is 0.48 minus 0.75 minus 0.56. Now all the nodes are in equilibrium, so we ignore the carryover moments and we can calculate the final moments. Let's remember how we calculate the final moments. So let's start from node A. At node A, I got 128. This is the case when all nodes are clamped, so no rotation at B. So at the first cycle, we see a rotation, and due to that rotation, I see a moment that's equal to 11.98. And then in the second cycle, due to the additional rotation, I see an additional moment. Magnitude is 2.2, and so on. I will add all these effects and obtain the final moment. So in my calculations, I have 4 cycles. So these results belong to the 4 cycle solution. minus 97.15, 97.14, minus 83.81, 83.81, and of course 0. So these are the final moments at the member ends. Let's remember how we obtain final moments. Let's repeat one more time. So let's take a look at node C. This is minus 72 is when there are no rotations, all degrees of freedoms are equal to 0. We release, we allow C to rotate. So due to that rotation, we see a moment. Rotation at C, that moment is minus 20.59. But node B also rotated, and due to that rotation, we see an additional moment here that is 16.01. So this is the results after the first cycle. Now, after the first cycle, still I have some unbalanced moment. Now, distribute it one more time, release the nodes. So when I release it, I got minus 9.16 at this end of the member due to rotation at C. B also rotated, and this 2.94 is due to the additional rotation at B. So we add all these numbers, all these effects, and obtain the final moment. So as I said, this is a more practical method. We distribute all the moments at the same time. We calculate all the carryover moments at the same time. Of course, mechanically this doesn't make sense, but mathematically it is equivalent to what we were doing before. So this finalizes the solution of this continuous beam, and we will have more examples. Now there's another example problem that we will be working on. Now this is a little bit more challenging because now we have a cantilever and we have to figure out how we can handle this cantilever. So for that, let's do discretization first. Try to understand the structure better. So in node A, if I can draw it, member AB, node B, member BC, node C, member CD, and node D. So the degrees of freedoms, I have rotation here, theta A, and translation here, delta A, rotation here, theta B, and rotation here, theta C. So it looks like we have 3 degrees of freedom, and in addition to that, I have a translational degrees of freedom at the tip of the cantilever. But now when we have a cantilever, there are always buts. So let's draw the Freebody diagram. So member AB, member BC, CD. Let's show the forces. Member load 14.4. I have a, let's erase that, not show it in here. Let's show it on the node. So I got 15 kilonewtons here. Now let's write down everything that we know. So here 15, I got 15 here. So this moment should be equal to 15 times 4, 60 kilonewton meters. And there are moments here that we will try to figure out. Now when we look at the cantilever, actually it does nothing but transfer this 15 kilonewton to node B as a vertical force plus a moment, 60 kilonewton meter moment. So it doesn't matter what the value of displacement translation at A or the rotation at A is, these forces will not change. So as we did in the moment distribution, we can eliminate that. No need to calculate, no need to worry about these two translations. This means that we can actually forget about the cantilever. The only thing that we should be considering in our calculations is this 60 kilonewton meters. Okay. Now, having said that, now let's continue our solution. The first thing that I need to do, again, calculate the stiffness factors. So I got member AB, but let's think it this way. Let's think about the meaning of the stiffness factor. It's the moment required to create a unit rotation. So if I want to create a unit rotation at this point, at point B, how much moment do I need to create a unit rotation? Basically nothing, because I don't have any resistance here. This end is free to translate, free to rotate. So it means that the stiffness factor for member AB is equal to 0. It's free to move, it's free to rotate, so I don't need any force. Okay? So what about the stiffness factor of member BC? So I will solve this problem in two ways. Now in the first way, in this solution approach, this is what I will say. Okay, I have a rotation degrees of freedom here. So this end is not free to rotate because I have member AB. I know that its stiffness is 0, but right now, this is the way I'm thinking. I got member AB. This end is not free to rotate. So its stiffness factor is 4EI over 10. Let's come to member CD. Member CD, I'm looking at this node. I have a rotation degrees of freedom here, and member point C is not free to rotate because I have member CB here. So the stiffness factor for member CD is equal to, again, 4EI divided by the length of the member, which is equal to 5. So these are the stiffness factors. Now let's calculate the distribution factors. Distribution factors. So distribution factor BA is equal to 0, right? Because the stiffness factor of AB is equal to 0. So distribution factor BA is equal to 0. Distribution factor BC is equal to 4EI over 10 divided by 4EI over 10 plus 0. That will give me 1. Let's continue. Distribution factor CB is equal to stiffness factor of member BC, which is equal to 4EI over 10 divided by the total stiffness at node C, 4EI over 10 plus 4EI over 5. Let's see if I can make an E here. I couldn't, so this is E. So that number is 1 over 3. So distribution factor CD will be equal to 1 minus 1 over 3. When it doesn't want to write, it doesn't write. So distribution factor CD is equal to 2 over 3. We calculated the distribution factors also. Let's calculate the fixed end moments, or the picture when we have no degrees of freedoms. all the degrees of freedoms are equal to 0, or let's say. So fixed and moments. So member AB, so we are fixing this and node B, member BC, node C, member CD, and node D. So I have a member load on member BC, 14.4, and I got 15 kilonewtons here. When we calculate the fixed end moments, here I have 60 kilonewton meters. This moment is 120 kilonewton meters, and that moment is minus or 120. Let's write it this way. We put the sign on at the table. So these are the fixed end moments. These are the pictures when there are no deformations. Now we can start the moment distribution. So for that, let's draw our table one more time. Point A, point B, C, and D. Distribution factors. Let's draw these lines. Point B, C, and D. So here I got 0, 1, 0.33, 0.67, and fixed support, this is 0, 0. These are the distribution factors. Now let's write down the fixed end moments. The fixed end moment here is minus 60, that's BA. The fixed end moment BC is plus 120. Fixed end moment CB is minus 120, and I don't have any loading on member CD. Remember that this is the case, all degrees of freedoms are 0, okay? Or you can just say that all nodes are clamped. This is the picture. Oops, let me erase these dots. And we can start the moment distribution. So distributed moment, release all the nodes. So here the unbalanced moment is plus 60, and here the unbalanced moment is minus 120. So distributed moments. So the cantilever cannot carry any loading, so all these unbalanced moments must be carried by member BC. So I have minus 60 here. Distribute the unbalanced moment of minus 120. 40 kilonewton will be carried by member CB, and 80 kilonewton will be carried by member CD. Carryover moments. So this one will go here, minus 30. Remember that we didn't use any modified equations. We say that the stiffness factor of KBC is equal to 4EI over 10. So we are not doing any modification. So that's why we will have the carryover moment to node B as minus 20. And the half of this 80 will go to node D. So this is the picture after the first cycle. So the unbalanced moments, the magnitudes of the unbalanced moments are 20 and minus 30. This is not small, so I should continue one more cycle. Distribute the moments. So 20 must be carried by member BC. So I have minus 20 here. Minus 30, 10 will be carried by member CB. 20 will be carried by member CD. So this is the distributed moments after the second cycle, and do the carryover moment. So minus 10 will go here, 5 will go to node B, and 20. So this is the case after the second cycle. So the moments are not small enough. Distribute the moments, minus 5, so 3.33, 6.67 distributed moments, and carry over moments, half will go here, 1.67, this half will go here, minus 2.5. So we will continue this way a couple of more cycles, and at the end of the day the moments that we will be finding is as follows. Let me write it here. So MBA will be minus 60, MBC will be equal to plus 60. Let's write the units, kilonewtons meter. MCB is equal to minus 109 kilonewton meter. MCD is plus 109 kilonewton meter, and MDC is equal to 54.4 kilonewton meters. Also, I have to have this carryover moment here. This is D. So this is the final moments, and we can analyze it this way. But as you see, when we transfer moment to the node B, all the distribution factor is 1. It directly transfers back the half of the moment. So that's why we had to do a lot of cycle. Now in the next example case, I will again work on this problem. So I will try to shorten the solution. Same problem, but I want to solve it in a different way, actually much simpler way. Now, if you take a look at this node, okay? Now, let's forget about, let me erase this node, okay? If this was the case, if I have a structure like that, how would I solve it? Let's think about that. So at node B, if you look at node B, we can directly say that this node is free to rotate because we don't have any resistance coming from that cantilever to rotation. So node B is free to rotate, and I can use modified equations for member CB. But in this problem, we have a loading, that 15 kilonewton. So the question here is, how can I handle this 15 kilonewton? Because it's a load. But when we write the stiffness factor, we don't actually worry about the loads. We said that it's a structural property. So while writing the stiffness factors, we forget about the loads. Now, if I can solve, how can I handle the moment created by this 15 kilonewton? I can actually analyze this structure in a much simpler way. So let's try to do that, okay? So again, I will do discretization, okay? I do it because it helps me to think, it helps me to understand the behavior of the structure. So every time, even if everything is straightforward, I prefer to draw it. So it's always a good idea to draw it, okay? Let's forget about the cantilever. If there's no loading, for us it doesn't exist. So I have a rotation theta b and a rotation here theta c, and for me, let's put a note. This is free to rotate. I'm forgetting, I don't worry about the loads right now. I'm just looking at the structure. This is free to rotate, and I can use modified equation for member BC, which tells me that I can actually solve it by using a single degrees of freedom, which is the rotation at C. So that's the way I will try to solve this problem. So, stiffness factors. Let's determine that, stiffness factors. So I'm not worrying about KBA. Stiffness factor of KBC, so we decide to use the modified equation. Then it's equal to 3EI over 10. The stiffness factor for KCD doesn't change. It's equal to 4EI over 5. Now the distribution factors, distribution So distribution factor CB is equal to 3EI over 10 divided by 3EI over 10 plus 4EI over 5. So that gives me a distribution factor equal to 0.273. Then distribution factor CD will be equal to 0.727. So this is the distribution factors when I say node B is free to rotate. Now let's calculate the fixed end moments. So let's draw the pictures. This is member AB, node B. Remember, we are using the modified equation for member BC, so I just show it as pin here and fixed here. Node C, fixed and fixed, and I got 15 kilonewton here. Now actually it doesn't matter what I show here, because that moment will always be equal to 60 kilonewtons. That always be equal to 60 kilonewton meter. It doesn't matter how much rotation I get, if it is fixed or not, right? At member BC, I don't have any moments, so all the moments are right here, and this is 180 kilonewton meters. So this is the picture now. Let's start the moment distribution. Oops, wrong color. Let me choose black and then draw it. Point A, point B, C, and D. Again, let's show the distribution factors. So distribution factor for this one is 0. This is 1. Distribution factor CD is 0.273. Distribution factor is 0.727. 7, and this is fixed support 0. So I will just use all nodes are clamped. Fix end moments. Let's write it down. So here I got minus 60 and minus 180. Now what I'm going to do is release node B. Now when I release node B, what will happen is, due to that load coming from the cantilever, I'll see some rotation, and due to that rotation, I'll see a moment on this side of member B that's equal to 60. So this is the distributed moment due to rotation at B. I'm still avoiding the rotation at C, so it's still fixed. So I have carryover moment due to rotation at B, so half of this moment will go to node C. So I'm actually done with node B, because remember that we said we will be using the modified equation for member BC, meaning that I don't have any carryover moment from C to B. They always be equal to 0. Node B now in equilibrium, and the final moments, I will just write it here, for node B is minus 60 and 60. So we are done with node B. We can forget about it and we can deal with the rest of the structure. Now let's release node C and see what happens. Now I got 180 due to the distributed load and plus 30 due to the rotation at node B. So the total unbalanced moment is minus 150. So distributed moment at C minus 150 times 0.273 will give me a moment that's equal to 40.95, and that moment is 109.05. Now we have rotation at C and carryover moment. I don't have any carryover moment from C to B, so it's done. So the half of this moment, 109, should go to the 54.52, and now all the nodes are in equilibrium, and the final moment for node B is, I got 40.95, 109.05, and 54.52 as my final moment. So basically what I did here is I look at the discrete version of that structure. I didn't see any loading. There's no loading. I'm just trying to figure out the property. How does this structure behaves? And I know that this cantilever has no effect, has no resistance to rotation, cannot provide any rotation to node B. So I'm using that information. And for that, I said that I can use the modified equation, and I'm saying that node B is free to rotate. So I have written all my equations accordingly. Calculate the stiffness factor using the modified equation. Calculate the fix end moment using the modified equation. So the only problem that I have to solve is handle this moment created by this 15 kilonewtons. But I know that this part of the structure is statically determinate. So it doesn't matter how much rotation I get at node B, that moment is always 60 kilonewton meters. So when I put it into moment distribution approach, if I have minus 60 here, at member BC I should have plus 60. And I know that if there's a moment at node B, half of that moment will go to node C, plus 30. And then I'm done with node B. The rest is just the same procedure. Do the moment distribution to the rest of the structure. We are done with node B. In another point of view, actually, what I did is I calculated the fixed end moment, CB, due to the applied loading at the cantilever. So this 15 kilonewton created a fixed end moment equal to 60 at B, and half of it will go to C. So the fixed end moment CB due to the point load at the tip of the cantilever is equal to 30. So with this approach, I actually simplify the solution significantly. The structure comes in equilibrium in only 2 cycles. If you understand what we are doing here, you're actually done with the moment distribution. You understand everything that we discussed.